My name is Ashley Heredia, and I'm a transportation engineer too at a state governmental entity. I've been an engineer here for about 2.5 years, and before that I was a project engineer for Quest Global, but most of the work I did there was mechanical, as they're an outsourcing firm for Pratt & Whitney, and I worked there for about 1.5 years. So my experience as an engineer is not very advanced, as I have not been practicing for that many years. Today I'm going to be presenting on a load rating of a complex structure. The seminar will be a detailed modeling and review of the load rating results using MIDAS Civil. And I just want to add on that this presentation is more geared towards beginners, as I myself have only been using the software on and off for about 1 year. The model itself is a bit simplified. You can get into a lot of detail with MIDAS, but for the purpose of the rating, I wasn't as concerned with how the connections looked. I was just more concerned about the connections working properly. So the way the presentation will go is, first I'll give you a brief introduction of the bridge that will be modeled. I will also show you where to gather all the data that you will typically need to model the bridge. Then we will proceed to the actual bridge modeling and analysis. And after that, we will be doing the load rating section of it, and we'll also be going over some load rating troubleshooting. Finally, I will just do my best to try to answer some of your questions. Alright, so the bridge is located in Connecticut in the town of Glastonbury. Here's a map of the bridge itself. It carries Route 3 over Route 2, and here's an aerial view of the actual bridge. The bridge number is 5561, and it was built in 1987. So it's not a very old bridge. There has been no major rehabilitation done to the bridge since it was built. Now the project is actually a pavement preservation job, for which this bridge was 1 out of 9. And the only work that needed to be done here was the repaving. So the bridge was actually modeled to determine whether or not it could carry the loads of the miller and paver. This superstructure is currently rated as 7, so it's overall in good condition. Here on the top right, you can see a picture of the underside of deck, and on the bottom you can see the deck deterioration. I just want to point out in particular the map cracking and the joint deterioration, which is what the repaving was done for. The bridge is a curved 2-span continuous bridge comprised of 4 tub girders, and the total length of a structure is 278 feet. The first span is approximately 137 feet, and the second span is about 136 feet. Here you can see a screenshot of the bridge elevation and a screenshot of the plan view. Alright, so let's get into how and where we gather the bridge data from so we can model the actual. The first thing you want to do in your plans is go to your plan sheet, and you're going to want to gather the skew of your supports, the radius of the structure along the baseline, and where the fixed and expansion bearings are located. That's obviously going to vary depending on your bridge. You may have different types of bearings. From the cross-section, you're going to want to get your deck out to out as well as your curb to curb. You're also going to want to get the spacing between the girders. And from your elevation, you're going to want to get your span lengths along the baseline, which is important to note because basically your girder lengths might change based on where it is in respect to the baseline. You're also going to want to get from your cross-section the concrete slab's thickness in more detail, the distances between the girders, as they may vary, as you can see here. Now I just want to point out that you might not find this information exactly in the same places I'm getting them from, because it depends on where the plans were made and also what state you're in. But overall, this information should all be there. Now from the framing plan cross-section, we're going to gather the width of the bottom flanges as well as the distance center to center of your top flanges. You're also going to want to get the types of sections used for the cross frames and diaphragms and lateral bracings. And you will also need the distance between them, as I highlight here. Then from your general notes, you're going to want to get your material properties. So you're going to want to know, go in and grab the type of concrete that was used, the reinforcement and the steel, and all of the strengths that are assigned to them. I also want to point out that you want to get your girder depth for like the web and the angle that it was placed at, because later you're going to go in and you're going to calculate the distance along the web where all your nodes would be for all of your cross frames and end diaphragms. It's very important. You're going to want to get these distances from the center of your girder to where the node would actually be, which will later be used for part of the modeling of the bridge. So I use Microstation. You can also do this in AutoCAD, of course. For Microstation, we'll just have to save it as a DXF file to be able to import it into MIDAS Civil later. All right, so what I did first was model the baseline in Microstation using the radius of the structure. Here you can see the radius line. Then I offset this baseline to all of my locations where the center of the girders would be, as you see in red here, which you can find this distance in the framing plan typically. I also offset the baseline to reflect the deck edges, basically the out to out, these two red lines here. Here you can see them, and here's all my center line for girders, this one, this one, this one, and this one. And I also use the radius of the bridge to generate the lines that represent where all the cross frames would be, as they are perpendicular along the curve. So I want to point out that this was done in 2D, not in 3D. You can do this in 3D as well. For me, it's a little bit easier to do it in 2D to actually visualize it, and what I'll do is I'll offset all of the nodes in MIDAS later. I also want to point out here, these three lines that you see here are actually offsets from the center line of each girder. This is the center line. And they represent where the nodes will be for the cross frames, if you were looking at it from the top or the plan view. That's what we calculated before in the previous slide, where I showed you the base, that it was based on the angle of the web. I also want to note that because MIDAS Civil is not able to import B-splines or curves, you're going to have to break up the curves. So rather than making all of these tiny little lines for the curves here, what I did is I broke up the cross-frame distances. You can see each individual line here, instead of this whole thing being a line. And I also created a break on the curve itself for where the element would have to change to a different section. So for example, where the longitudinal stiffener starts, that'll be a break on the curve. And what I'm going to do is I'm going to bring in these nodes into MIDAS. I want to import the nodes versus importing the actual elements because the tub girder is a little more complicated, in particular because of the cross frames being in the interior and exterior. If it was an eye girder, it would be a little bit easier but to import the elements as well, but because it's a tub girder, it's a little more difficult. Now that being said, you can do it. I just prefer to import the nodes. So after you break up the lines, you're going to save them. You can see all of the different line colors or different layers. So like the blues are my cross frames, the white are the girder, and the red is the deck. So I just want to point out here that the line along where the supports are going to be placed, these ones along the abutments are also broken up, and the ones along the pier, which is this angled line here, and that's based on the skew that we got from the plan sheet. And it's important to note it because you're going to need to know where it is once you bring it into MIDAS. Now you're also going to want to know what scale you work in. This is very important because you're going to do a file save as, and you're going to select DXF file. Now if you're using AutoCAD, you can skip this whole step basically, but then you're going to have to pick the units that you use to create the model. So these will have to match up in order for the scale to be proper. These also have to match up your MIDAS model. So after you save that, you're going to go into MIDAS, and you're going to click on the MIDAS model here, and then you're going to click import and AutoCAD DXF file, and you're going to get this pop-up box here from where you're going to browse the file, and you're going to be selecting all of the layers that you used to create your model. Now it's important to know here you want to make sure you click on node, and you want to make sure these two boxes down here are checked because you don't want So when you create the model in Microstation, you might have duplicate nodes or lines, and you just want to make sure that MIDAS merges them all into one. You don't want to have like floating nodes that are not assigned to anything. So once you bring it in, this is what your model is going to look like. You can kind of get an idea of what the bridge itself looks like, but it's basically just the nodes. So if you click on this button here, you're going to see the elevation of the bridge. And I just want to point out, because it was made in 2D, you won't be able to see any depths. It's just a flat line. But what I'm going to do now is I'm going to go back and calculate the distances for all of these nodes in terms of the z direction, so basically all of the depths. So we're going to do this based on the concrete slab thickness, the haunch depth, and the actual depth of the web. You're going to find the offset distance from the top of the slab to the bottom chord connection. So this node right here, basically. In my case, it's 5.417. So you're going to go back into MIDAS, highlight all of those nodes that are for those cross frames. Once you highlight them, you're going to go into Node, Element tab, and you're going to click on Translate, and you're going to click on Move. And here you're going to put the distance you calculated. Make sure it's in the negative z direction, because obviously we want to go down from the top of the slab, not up. And you're going to click Apply. And if you click back again on this elevation button here, this is what your elevation is going to look like. You're going to repeat the calculations as well for the top of slab to top chord connection. In my case, it was 1.25. And I also want to point out that you're going to want to know the distance from the center of your girder to these nodes as well, which we had calculated previously. Alright, so you're going to repeat this process, and you're going to go into Node and Elements Translate and pick the new distance you calculated and click Apply. So basically the same thing we just did for the bottom chord. And once you do that, this is what your model should look like. Right now it's just a bunch of nodes. There's no element created. But you kind of get an idea of what the shape would be for the actual model. And now that you're here, you're going to highlight all of the nodes. And because you're going to want to merge and renumber all of them. I know we did click on merge nodes at the beginning when we imported them. But for me, it's just kind of like a safety check. I'll just re-merge them all and make sure that there's no duplicates. And then we also want to number the nodes consistently so that the program doesn't have to jump back and forth when it's running the analysis, as it might give you erratic values. Alright, so now that we have all of our nodes, we're going to assign their material properties as well as their section properties and thicknesses. So you're going to go into the Properties tab, and you're going to click on Material Properties, and you're going to click on Add. Once you do that, you're going to get this table here, the Material Data Table. And I just want to show you this in MIDAS real quick. Just give me 1 second. So you're going to click on Properties, Material Properties. You're going to click on Add. And you're going to select this type of concrete that you're using. In my case, is grade C3000. Now I just want to point out here that you can't edit anything in the concrete section. So what we're going to do is you're going to go back here into your concrete type, and you're going to click on None after you have originally selected it. And you're going to go down to your weight density, and you're going to make it 0. And you're going to click on Apply. Now the reason for doing that is because when we created the composite sections of the girders, it's going to have a material in there as well for the concrete, so we just want to make sure that the concrete weight is not being accounted for twice. Alright. So you're going to repeat this process for your composite material and for your steel material. Alright, so now we're going to go and create the actual sections. So going to Section Properties, click on Add, and under the DB User tab, you're going to select all of those different cross-sections and bracings you found on your plans. It's pretty straightforward. You just click on the tab and select the section that it is. In my case, I have some angles and a couple of WTs. Now, it's very important. This is my detailed sheet for all of my girders. You're going to want to notice all of your lengths for the different sections because these are going to have to be individually generated. See here where the top flanges change in thickness or width. That's going to be its own section. Also where like the longitudinal stiffener is, that also has to be separated from all of the other sections. So yeah, you're going to want to know all of the distances separately, and you're basically, each girder is going to be split into different sections because MIDAS doesn't let you create one huge girder with different thicknesses and widths all along. So what we'll do is we'll make a bunch of different girders and kind of join them into one. Alright, so now we're going to go again into the Properties tab, and you're going to select Section Properties and click on Add. And now you're going to go into the Composite section, and you're going to click on Steel Tub Type 1. That's the girders that we have for our structure. Here, I'm going to go into MIDAS now, so I just want to point out a couple of things. Okay. So basically this information here is all of the information that you gathered from your plans. So your tributary width of slab, the thickness, the height of the haunches, the depth of the girder, all of the, basically all of the individual parts that make up that girder. And then because all of the node distances we calculated are based from the top of the slab, not the center of the section, what we're going to have to do is we're going to go into change offset, and here you're going to click on center top. That way your main node is going to be at the top of the slab, which is what we had calculated for everything else. Alright, so I also want to show you what the stiffeners look like. If you click on stiffener here, you can add any type of, there's 3 different types of stiffeners we can add. We have T stiffeners for our longitudinal stiffeners in this model. So you'll just get all of your data. If it's just a WT section, you can just look it up and add it in here. And then your distances are based off of each other. So like if your first T stiffener is, say, 1.5 feet from your center line of web, then your second stiffener is going to be off of your center line of the first stiffener. So just wanting you to keep that in mind when you're modeling them. Alright, now we want to create our thicknesses. So let me just go back here. For the slab thickness, you're going to go to Properties, click on Section Properties again, and go over to Thickness tab. You're going to enter the thickness of your deck, then click on Offset, plate offset right here, and click on Value, and you're going to type in half of the thickness of the slab because, again, it's going to place it in the center of the node, and we don't want that. We want it to be offset to the top of the node, or to the top of the slab, basically. That way it'll, like, the whole structure is going to line up properly. Alright, now we can actually create the elements. You're going to go into Node Element, Create Element. Angel, is that you?
No.
Yeah, sorry, I just keep hearing some background noise.
No, I'm muted. Go ahead.
Okay. Alright, now we're actually going to create our elements. So you're going to go into Node Element tab and click on Create Elements. And make sure you select your composite section for this and select the appropriate section that you created. And what I want to do is click on the center node here, which is where the girder starts, and drag it over to where you want the element to end. So in this part, I just want to point something out, that because it's a curved girder, when you're creating your elements, you are going to want to make sure, here I'm going to show you real quick. So you're going to select composite and you're going to click on whatever the section is supposed to be. And basically, because when you go straight ahead, it's going to skip all of those nodes that are not highlighted. So what you're going to want to do is click individually at every node to make sure that they're all accounted for. Okay. So once you finish that, this is what your model is going to look like. You can see all of the different sections that we created. So this would basically be a lot easier if we had imported the element from Microstation, which is something you can do when you create the model. But because it's the top girder, like I mentioned, it's a little bit more difficult to just import those elements. So now we want to do this for the cross frames and the end diaphragms as well, since we have already moved the nodes down. Here you can see what it should look like once you connect them all. One thing that I want to point out is that when you're creating your cross frames, it is important to create them as a truss section versus a general beam. So here under element type, you can click down and select truss. Because if you create it as a general beam, you're going to have to assign each individual cross-frame beam end releases, which also get assigned based on the direction of the element. This can be pretty intricate, and the easier approach is to just model them as truss sections. You're also going to want to assign groups to all of your elements of your structure. It makes it a lot easier to work in the model because you can manipulate the model through these groups. So I clicked on the works tree and I highlighted the sections I want to group together. So say if you want to group all of the different elements for girder 1, you can go into the elements tree and display all of the sections you want to group. And you can, once you click on girders, it'll have that assigned girder. So what you can do is when you click structure group and create the new group, you can click on it and drag it into your screen, and it'll basically be assigned to any nodes and elements that have been highlighted in the model. You're going to want to group your cross frames and your slab as well. You want to make sure you assign groups to everything because, like I mentioned before, it's just a lot easier to manipulate the model. All right, now we're going to assign boundary conditions. Here's what all the groups look like. So you're going to go into your boundary tab and click on define supports. And after you have created all your groups, for my boundary groups, I just made a substructure support. When you go into boundary group name, you'll just have to select the group that you assigned. And you're going to highlight all the nodes that you want to have this particular boundary condition. And you're going to click on the boxes that simulate the particular restraint that you're looking for for those particular nodes. So if it's fixed, you want to restrain in all of the directions versus if it's just restrained in the Z direction for like an expansion bearing or so. So after you do that, you're going to assign your rigid links. This is to connect all of your cross-frame nodes to all of your girder nodes. So let me just open MIDAS real quick and show you. I just want to show you how the rigid links works. So you're going to click on boundary, rigid link. It's going to ask you for a master node number. That's going to be your girder node that you want connected to those cross frames. And then what you're going to do is you're going to highlight all of the nodes that are in the cross frame. you're going to click on rigid body and you're going to click apply. This will connect all of these nodes to that main node, and it'll ultimately look like that. Alright, there you go. Those are the rigid links. And you're going to repeat that process for all of your cross frames and your end diaphragms as well. Alright, now we're going to go into your load tab and click on static loads. And then you're going to click on static load cases. And this is where you're going to create all of your dead load cases. So here you'll want to add on your self-weight, your wet concrete, your formwork, barrier loads. If you have a median strip, you want to add that, all of your connection plate loads, and your wearing surface as well. If you have any utilities, you can add that on here as well. Alright. Once you do that, I'm just going to go into MIDAS and show you. So once you create all of your static load cases, you can click on self-weight, and you're going to assign it in the negative z direction. So you can just type -1 so that it does one times that load, and then click add, and that'll assign it to all of your material. Then you can go into your element right here, and you are going to assign like your all of your other loads, basically your wearing surface, your wet concrete, your formwork. So say for example it's negative, let's say 1 kip, just as an example. You're going to highlight your girders and you're going to click apply, and it's going to assign that load to all of your girders. You can also restrain it to apply it just to, like, say your fascia beams versus your interior beams, or if you have the load just in one particular place, you can assign it to that as well. Alright, now we're going to move over into our moving loads. So you're going to click on moving load and traffic line lanes. You're going to get this menu here, and you're going to pretty much fill it out. Just assign your lane name, then you're going to assign your lane width. I use 10 feet. You can also click on lane optimization so that MIDAS can select like the worst case in the lane. And what you're going to want to do is you're going to want to run it through your cross beams, and you're going to select your deck on this group here. So what it'll do is it'll transfer the load along the deck width. So another thing I want to point out is that if you made your deck here from plates, what you can do is create traffic surface lanes. It'll be based on the surface of the deck instead of individual line lanes. So now the way I selected it is I click on number down here, and what I do is I highlight all of the nodes at the edge of the deck, these nodes here. Once I highlight them, they're going to show up on this box, and you're going to click on, basically just going to copy it over to this number tab and click on add. Once you do that, you're going to want to look for where your second span starts. So say it's this node over here, so you're going to want to see what node number that is, and you're going to search it in this section, and you're going to click the checkbox for span start. That way, basically MIDAS will know where your new span starts. Alright, now you're going to go over into your vehicles tab. If you're using standard vehicles, you can click on Add Standard and pick ASHTO LRFD load. Here you're going to find all of the HL93. Then if you click on ASHTO standard load, you can get your HS20s. And lastly, if you click on ASHTO legal permits, you will find all of the legal loads here. And make sure you're adding your dynamic load allowance here. You can see it in this tab. It allows you to do it. Or if you want, you can click on Add User Define, and here you can make your own truck. Usually the contractor will submit a truck configuration, and you can use that to generate the truck here, which is what I did in this case to be able to check if the miller and paver loads were being, if the model could carry them, those loads. Excuse me. Now we want to go into lane support and click lane support negative moment, and you're going to assign it for all of your girders. And we want to do this because of this bridge is actually a two-span continuous. Alright, now you're going to go over to your construction stages. Click on Define Construction Stage. This section is really for analyzing the bridge's reactions while it's in construction, which we aren't really concerned with since the bridge is already built, but we do want to add some stages so that we can properly assign the deck loads. And we do this to make sure the deck loads are accounted for in the load rating section. So I'll just briefly explain. You're going to go click on Define Construction Stage, click on Add, and you're going to get this like pop-up box here. You can give it a duration and assign all of your element boundaries and loads that you want to be activating during that particular stage. It's important to activate all of the elements and boundaries as well as to assign all of the loads. In particular, I want to note that you'll want to activate the wet concrete load in an initial stage, obviously after your girders are activated. And then you'll want to deactivate this load in a subsequent stage in which the deck element should be activated. This is because the load will be accounted for in the composite section itself. So let's go over activating this load. If you click on composite section for construction load, for construction stages, and click on Add, here you're going to select the active stage. And for our girders, that would be stage 1. And then you're going to select the section that you want to activate it. Keep in mind you're going to do this for all of your composite sections. Then under construction sequence, you can select the material and in what stage you want that material to be activated. And for the deck, you're going to want the concrete to be activated in the same stage that the wet concrete got deactivated under our construction stages. So in this scenario, it was in stage 3. And then you're going to click OK and then repeat this for all of your composite sections. Alright, then we're going to go over to our Analysis tab and click on Main Control Data. And you just want to make sure that you have all of these boxes here checked off. Then we're going to go into our Moving Load Bind, and you want to make sure that you have your stress calculation and your combined stress calculation as well. If you're using the analysis side of it, basically if you were reviewing the results from the analysis in detail, then you would want this. We're not as concerned, but for the load rating aspect, I'm just going to work with the values directly from the analysis. I'm going to work with the values directly from the load rating section. Alright, so you're going to click next in the construction stage tab, and what you want to do here is you're going to click on this button right here to add erection loads, and this is basically to differentiate all of your erection loads from your dead load, from your self-weight basically. So you can have all of your DCs in one erection load and all of your DWs in another one, like your wearing surface and your utilities versus your formwork and like all of your additional steel and so on. So after you do that, you can run the analysis. You can either click on this button right here, or under the Analysis tab, you can just click on Perform Analysis. Here you're going to be able to see all of your deformations, your forces, your reactions, basically your moment, your shear, and all of that type of data. And you can also see how your structure is going to basically deform or like deflect. Alright, so up to this point, we've covered all of the analysis section of the modeling. Now what we really care about in this particular presentation is the load rating part of it. So we're going to go into the load rating tab, and you're going to click on steel bridge, and you're going to click on steel rating design code. So this part is pretty straightforward. You can just kind of follow the steps down the line here. So you're going to click on ASHTOY layer of D12. And that's one thing I wanted to point out. The code MIDAS runs right now is not entirely up to date. So if you need to use the latest code, you'll have to go in and calculate the values yourself, or at least check the equations that have changed since that last code, to make sure that you're getting all the correct values. So you click on rating parameters and make sure we are on multiple box sections, and we want to take into account all of the strength limit states, and we include fatigue as well, as you can see this button here. Alright, now moving on to rating group setting. We want to rate our girders, so from your groups you're going to pick your assigned girders group and add it here, and you can check either one end of each element, so in other words either the I or the J end, or you can have MIDAS check both ends of each girder, or each element in particular. Keep in mind that the more elements and more ends you have the model check, the more time consuming it can be for MIDAS to provide these results. In addition, you're going to have a lot of information to run through. Alright, next we're going to click on rating material, and here we're going to modify the composite material to include the grade of the reinforcement. So if you highlight the composites material here, it'll allow you to edit these boxes here, and you can basically select the grade of the steel that you have for your reinforcement. In my case is grade 60. Right, the next step will be to assign the longitudinal reinforcement. Here's where you will put all of your rebar. This is something you can also do before the analysis is done, or you can do it in this section here. If you need it before the analysis, then you're going to go, I'm going to show you into your MIDAS model, and you're going to click in Properties, Section Manager, and Reinforcement. And this will give you the exact same table that is on the load rating section. Alright, now you go into rating, click longitudinal reinforcement, highlight the first section and to be able to add the reinforcement to. There's a couple of ways to add the rebar. You can do it as a line or as individual points, so any of these sections here. And I do it as a points just because it's easier based on the values that I got from our plans. So if you go to your bridge cross section, it should have all of the reinforcement data. It'll tell you your distances, which you can use to generate the reinforcement here. It also will tell you what size rebar you need. So you can click on point here, and it'll ask you to give you the reference distance from this point, which is like your center of girder. But what you can do, and I'll show you in MIDAS, is you can click on coordinate left bottom so that your like 0, 0 coordinate is actually at the corner of your girder section. This might make it a little bit easier for you to calculate what the distances should be. So you can type in the distance from this point, and then you can select the girder or the rebar size that you need. Click on add and repeat this process for all of your rebar. Now what you can do, if you have the same reinforcement layout for all of your girders, you can click on copy reinforcement tool, highlight all of the sections that will have the same reinforcement and bring them over to the side, and click OK. Before you do anything else at this point, you want to make sure you click on apply. It's not going to close this window, but what it'll do is it'll kind of save it into all of those element sections. And it's important because if you don't click on apply and you go ahead and click on another section, it's going to like automatically erase those reinforcements that you just assigned. So make sure you click on apply before you move along. All right. Let's go back here. All right, next you're going to go into position for rating output. And again, here you can select either your I or your J, or both your I and your J, and you're going to select, you're going to highlight your girders, because we want to rate our girders, and then you're going to click on apply. You can go to steel bridge again and perform your rating design. This should not take too much time. The Excel report is a little bit more time consuming, especially if it's for the entire structure. Alright, so let's click on that Excel report. It's going to prompt you to save it, and then it's going to run the report. If you selected all of your girders, all of your elements in both I and J sections, it might be a little time consuming, so just keep that in mind. But this will give you a detailed rating on all of the sections and all of the trucks. So once you do that, this is what the report looks like. Here you see the load rating result table, which has the summary for basically your worst case scenario ratings. And it'll also tell you like all of your critical elements where this happens. Alright, so I want to point out here that my shear is basically pretty much failing for all of the cases. And here's where we're going to get into the troubleshooting part of it. So the reason why all of my elements are failing for shear is because MIDAS in the load rating section, when it's calculating the shear, is not technically accounting for both of the webs in the tub girder. Is only accounting for one of the webs. So what we want to do is we want to go in and make sure that these capacities are getting added on. So what you can do is you can click on the individual sections. This is each particular element, and you can see what the capacity, what the dead load demand and the live load demands are. And this is the information that we're going to need to be able to troubleshoot. Alright, so now we're going to go into back into the steel bridge section here for the rating, and you're going to click on rating design results table and click on the service limit state summary. Basically you're going to get this table right here, which is kind of like the raw data for all of the information that you're going to see in your Excel report. It's just more in detail, and it's just more straightforward when you see it in the Excel report itself. So if you go back and you click on rating design results table and click on shear strength rating detail, here you're going to select all of the elements, the parts, and the trucks that you want to check or that you want to correct. Again, keep in mind this is a lot of data, so if you know which particular element you're worried about or what section you're worried about, you can just focus on that one. But if not, you can also do it for all of them. So you're going to get this table, and you're going to right click and hit copy. Then you're going to open Excel and paste it into your Excel file. And at this point, what you're going to want to do is you're going to add on 4 new columns for your new dead load, your new live load, your new capacity, and your new rating factor. And once you do that, you can highlight that row with all of the main names, and you're going to pretty much click on sort and filter here so that you can pretty much sort them later from lowest to highest, and you can see what your lowest ratings are. Alright, under your dead load, you're going to click on that first, basically the first box, the first cell, and you want to do the absolute value for all of your DC factors, the DC before and the DC after, as well as your DW. Make sure you are multiplying your factors by your loads, and then you want to divide this by the cosine of the angle of your web. The reason why you're doing this is because the web is angled, your load is actually going to be a little bit higher, so we want to make sure we take that into account. And then you're going to repeat this for the live load. And you're going to want to multiply your capacity by 2 because we have 2 webs, not just one. And then you're going to go over to your rating factor cell, and you're going to pretty much subtract your dead load from your capacity and divide it by your live load, which is just your standard rating factor equation. And then you're going to drag that over all the way down to the bottom of your sheet to make sure you have all of your sections. And then once you do that, you can sort it, and it'll give you your lowest rating factor, your new lowest rating factor. All right, so that's pretty much all I have.